Hello everyone, my name is Andrea, and in this video I'm going to show you how to build a fit in Python, and more specifically, with this video I'm going to comment on the article that I already written on the polyfit function, which is a function of NumPy that allows fitting multiple data points with the polynomial functions. So in this video I'm going to show you two types of fit. The first will be a linear fit, which is kind of the simpler one, and then I'm going to show you also an example for second degree polynomial fit. So just to begin, what we mean with the fitting procedure? Well, when we are fitting some data points, we are basically trying to define a mathematical function or a curve that is describing a set of data points that we have collected from, for example, previous experiments or measurements, or just from other sources. The aim of curve fitting is to obtain a quantitative description of these observables. When we define a fit, there are some pretty advanced techniques that we can employ. We can, for example, add some constraints to our fit functions or provide some guess values in order to lower the computational weight for the machine. But we will not see all this stuff. We will just stick to the basic definitions of fitting and of the NumPy polyfit function. So just to begin, we import NumPy as np. I also import this function from NumPy, which is called random, and I will show you in a moment why I'm importing this function. It will be used to generate one of our two array of data points that we will going to fit. And then finally I'm importing matplotlib as well, in order to be able to plot the fit and the points that I'm going to define. So as I told you, let's begin with a linear fit. So the first thing that we have to do, since we do not have points collected from measurements or from other sources, we will define two arrays of data that will represent our data points that we will try to fit. So let's begin with the X array. I will use the function, the NumPy function linspace, which basically generates an array of points once you have specified the start, the end, the ending value, and the number of data points that you want. So it basically take this range from 0 to 60, and it divides this range into 60 evenly spaced intervals, so 60 numbers, and this will be our X array. Now we have to generate in a similar way our Y array. I will not use again the linspace function, because in that way we would obtain an already straight line, and since we are trying to define a linear fit which consists of a straight line, it doesn't make sense to already have a straight line defined by our data points. So to introduce some noise and some fluctuations on the data, I will define the Y array in this way. I'll basically build a list, and this list will be defined as follows. So random rand int, which basically generates a random integer, and I can specify the lower and the higher value for the random integer, and I will take this I minus, let's say minus 2 and I plus 2 for I in x, and let me just convert it as a NumPy array. So what I've just done, basically I have defined a list with the list comprehension method, and basically in this list I take each value that is present on the X array, and for each of this value I will add or subtract a random integer that is within I minus 2 or I plus 2. So and this is done only to introduce some randomness on the data points that we have to fit in a second time. So if you're not comfortable with this definition, just copy that in your text editor and go ahead with the rest of the procedure. So this is our Y array. So what we have to do, well, I can show you, for example, how it looks like now, just to give you a glance of what I've done. X dot equal fig dot subplots. I'm just defining some functions for plotting what I've defined, and I will choose the X and the Y axis, and as you will see, what's the problem? Oh, here, rand int again, sorry, fig. Okay, now as you can see, it's not a straight line, but there are some points that are fluctuating, because for each of these points I'm basically choosing a random integer that is defined as the value of x of the x of this point plus or minus a random integer between -2 and +2. So in this way I obtain the fluctuation that I need to fit. So now let's make some space. These are the plotting function. What we have to do now is to apply our fit. So applying the fit, let's say a linear fit. Okay, so the first thing to do is to assign to a variable the function that we will use, which is, as I told you, the np.polyfit function, which, as you can see here, it takes as input the x and the y array of our data points that we are going to fit, and the degree. So the x, the y, and the degree in this case is 1, since we are defining a straight line. So as you may already know, the equation of a straight line is defined as y equals to m times x plus q, and in this equation m is usually called angular coefficient, and it's a parameter that describes the slope of the curve of the line, while q is called the intercept, and it describes basically the value at which our line crosses the y-axis. So when we apply a fitting procedure, a linear fit, we are basically trying to find the values of m and q that best approximate our data points. So the output of the polyfit function are these two parameters, m and q, the angular coefficient and the intercept, and the function will give this value in the order of the highest degree term. So for example, the angular coefficient is multiplied in the equation of a straight line by the x term, so it will be the first, and the intercept, which is not multiplied by anything, will be the last one. If we were to have a second degree polynomial function, which is defined as which is the first parameter multiplied by x squared, and then another parameter multiplied by x, and another parameter multiplied by anything, the first parameter that will be given by the polyfit function will be the one that is multiplied by the second order term, so by x squared, and then the other two in this order. So let's define our angular coefficient, and it will be equal to the first output of our fit, which is our polyfit function. We can define now our intercept in a similar way, and as you may have understood, it will be the second output of our polyfit function. What we have to do now is to define the fitting equation, which is the equation of the straight line of that straight line that have as an angular coefficient and as an intercept the values that we have calculated now by fitting our data points. So I will define, I will call it fit equation, and it will be equal to angular coefficient times x, which is our independent variable, plus the intercept. So what I have just done now is basically define this equation, m times x plus q. So it's the equation of a straight line that has the intercept equal to the intercept calculated by our polyfit function, and the angular coefficient equal to the angular coefficient calculated by our polyfit function. Okay, so basically we're done. We can proceed further with plotting what we have done. I will plot first our fitting function. So plot the x array, which is still our independent variable, and as the y array of this plot, we will enter our fitting equation. Let me just add some details like the color. Sorry, let's make it red. I will introduce some transparency as well, and let's also put a label for more clarity, linear fit. Okay, let me just complete also this here, which are our data points. So I can type here just to be more clear. This is our fitting function. Well, these are our data points. X, Y, let me define the size of the points, like 5. their color, let's go with blue, and the label, and I will call them simply data points. Perfect. Another minor thing that we can do is to set a title. Let's say linear fit example, and we can define also a legend as well, since we have inserted the labels for each of the two plots. And we're basically done. Let's compile, see what happens. And here we have our plot with our data points and with the linear fit, which is the red straight line. As you can see, the fit basically describes in the more close way possible the trend that our data points are referred to. And that's it basically with this first example. In the next example, as I told you, we will look at the second degree polynomial fit. So hope that this part was clear, and for anything else please comment below the article. Okay, now let's turn to our second example, which is referred, as I told you, to second degree polynomial fit, always employing the polyfit function of NumPy. So let's just make it polynomial fit. Okay, for this example, we're going to fit some data points that actually describe the trajectory of an object that has been thrown from a specific height with an initial speed in the x direction that is unknown. And I chose to use this example just to add some more, let's say, to have a more practical example, just to show you how fitting equations, fitting procedures are used in a real life situation, to understand a real set of data. So first of all, I'm in order to fit this trajectory, the trajectory of a falling object is described according to the laws of physics by a second order, a second degree polynomial equation. And the general equation for a second order, a second degree polynomial equation is this one: y equal to a time x squared. Oh, well, I can show you in the article itself. This is the actual equation that describes a polynomial fit of the second degree. And from a mathematical point of view, this function describes a parabolic curve. So let's go back to our text editor. I will just import, for simplicity, our set of data points. So they are the x array and the y array with all data points that describes the trajectory of our object that has been thrown. And now, as with before, we have to apply to call our polyfit function. So, and we assign the results of this polyfit function, the output of this function, to the variable called fit. So num.polyfit, and I will give it the x array, the y array, and this time I will choose a second degree polynomial function. Now we have to store in separate variables the outputs of this function, and as I told you, the first, as I told you before, the first output of the polyfit function will be the term that is multiplied by the highest degree term, the highest degree term in the equation. So a equals to fit 0, b equals fit 1, and c equal fit 2. A, b, and c, as I showed you, are these three parameters. As you can see, a is multiplied by the highest x, which is x squared, b by the x, and c it's not multiplied by anything. Okay, what we have to do now, very similar to the previous case, to define the equation, which is the one that I just showed you, by the way. So fit equation, and this time it will be a times I can use NumPy square x plus b times x plus c. Okay, now what we have to do is to plot our function, and to plot our function, basically we have to do this simple definition, subplots, and then I'll define first as before the fit, and so the x, which is our independent variable, and then the fit equation. Again, I will give it a color. Let's stick to the red. A transparency in order to see the data points, and the label, which this time is polynomial fit. In a very similar way, I can define a scatter plot with the data points, so the x and y array. Again, I'm defining the size of these points, the color. Again, we'll stick it with the blue for the data points, and the label, which would be data points. Okay, again we can just define a title just to add some more things to the plot. Polynomial fit example, and also a legend. Sorry, not set legend, but only legend. pt.show. If there are no errors, it should compile and show you, yep, the data points and the fitting function, which this time was a parabolic function that describes the trajectory of our object that is falling, and the data points basically in this case correspond to different positions in space and time of our object, of our falling object. And so in this way we obtained the plot, the fit, and we have plotted both the fit and the data points. What we can do now is to try to obtain some other information regarding these data points. So as I told you, these points describes an object that is actually falling from a specific height. The height will be given by this term according to the equation that you can find on the article that are related to the motion of falling objects. Well, as you can see, I can show you again on the article. This is the the equation from the classical physics that describes the motion of a falling object, in which g is the acceleration of gravity, v0, v0 is the horizontal initial velocity that we don't know actually, and y0 is the initial height from which the object is falling. So this corresponds to the only term that is not multiplied by the x coordinate, and which is the c value. So we can obtain this value just by typing, let's see here, we can print c, we can say like initial height, and we can go with this c, and what we get is this value 24.9, which is very close to the first point that we had. The most interesting thing is to calculate the initial horizontal velocity. Well, as you can see, an important thing is that the real equation that describes this motion, it hasn't got the term that is multiplied by x. In our case, our fitting procedure will give as an output also that value, but as we can check, which is the b value, this term will be very small, and so it will be neglected, but the fitting procedure will always give you a value for all the parameters, because it evaluates them numerically. So let's say b, let's say plus nb, and as you can see, b is very small. It's 0 times 0.38, which compared to the other can be neglected. We can just stick to this expression, which derives from this equation. As you can see, I reported here, for if you are interested in these problems, the Wikipedia link to check that. So we have to apply this equation to obtain this horizontal velocity, initial horizontal velocity. So we already know the acceleration of gravity, and we have calculated, our fitting procedure has calculated a, so we just need to compute the square root of minus g times 2 over 2 times a. So let's go back to our code. We just have to define the gravity acceleration, which is 9.81, and our v0 will be NumPy dot square root, and we set minus g over 2 times a. So if it's correct, the acceleration of gravity is negative, sorry. If this is correct, we will obtain our initial velocity, so initial horizontal velocity string v0. Let's see. Not a number. Oh, sorry. Yeah, because in the convention that I just used in the article, the acceleration of gravity was taken as a positive number because it depends on the definition of the axis. So let's try again. And here it is. This is the initial velocity, 6.97938 and other. So that was it. We've basically obtained the fitting of our data points. We've plotted them, and we also extracted some values, from some practical values, to interpret our fitting procedure. So I hope that also this second example was clear enough. Let me know what you think about it and in the comments, and how I could improve in this video commentary. Hope to make other videos and to help you with these functions. Bye bye.